All right, so today we're going to look at section 2.2, part 1, analyzing conditional statements. I apologize, but my stylus is not letting me work properly on this, so I'm going to try to type these up for you as we go. So this first part, I should say a conditional statement. A conditional statement is a logical statement that has two parts: a hypothesis and a conclusion. When a conditional statement is written in if-then form, the if part contains the hypothesis and the then part contains the conclusion. So an example of this would be, if you are a freshman, then you are not eligible for privilege time. We have different parts of a conditional statement. The very first one is called the converse. You can think of this as the conditional reverse, because this is where you reverse the hypothesis and conclusion, which just means they trade places. Okay? So you switch the order of it. Then we have the inverse. This is the original statement, but with nots. Because inverse means opposite. Okay? Then we have the contrapositive. This is the converse or the reverse of the original. So this is the reverse of original. Which just means that it's the original statement with knots. So let's look at an example of that. Okay. So it says, let's try to classify this as true or false. If false, we have to give a counterexample. So the original statement: if you're one of Ms. Haskins' third-hour students, then you're a geometry student. Is that true or false? Okay. Well, this is true. So let me see if it will let me circle this. So this is true. Okay. The converse of that, so we want to reverse the hypothesis and the conclusion. So the converse is going to say, if you are a geometry student, then you are one of Ms. Haskins, or we could say then you are in Ms. Haskins' third hour. We want to classify that as true or false. So if you're a geometry student, then you're in Ms. Haskins' third hour class, right? Well, we could say that that is false. Why is that false? Because I teach geometry first hour, second hour, third hour, sixth hour, and eighth hour. So a counterexample would simply be, you're in geometry in first hour. So now we want to do the inverse. The inverse is the original statement, but with knots. So the original statement said, if you are one of Ms. Haskins' third hour students. So the inverse is going to say, if you are not one of Ms. Haskins' third hour students, then you are not a geometry student. So there's our inverse. And now we want to say, is that true or false? Okay. So if you're not one of Ms. Haskins' third hour students, then you're not a geometry student. Well, again, we could say that that would be false, because, again, I teach geometry more than just third hour. So we need to give a counterexample of that. We could say, you are in geometry in Miss Haskins' second hour. So now we want the contrapositive. The contrapositive, remember, is the converse reversed. Okay, so it's where we take the original, okay, or we reverse the original and put nots in it. Okay, so the original statement, if you are one of Ms. Haskins' third hour students, then you are a geometry student. We took the converse of that and said, if you're a geometry student, then you are in Ms. Haskins' third hour class. So the contrapositive takes the converse and puts nots. So if you are not a geometry student, then you are not in Ms. Haskins' third hour class. And then we want to classify that as true or false. So if you're not a geometry student, then you're not in my third hour class. Well, third hour, I have geometry, so that would be true. So if you're not a geometry student, then you're not in Ms. Haskins' third hour class. Okay, because my third hour is geometry. All right, let's try that with another one. Okay, the original statement, if a figure is regular, then it is equilateral and equiangular. This is true, right? Because that is the definition of a regular figure. So now we want the converse. Right? And again, remember the converse, we just trade places with the hypothesis and the conclusion. So we're going to say, if a figure is equilateral and equiangular, then it is regular. Is that true or false? If a figure is equilateral and equiangular, then it is regular. Well, that's true, because again, that's the definition of regular. So now we want the inverse. So the inverse, remember, is where we take the original statement, but we put nots in it. So if a figure is not regular, then it is not equilateral and equiangular. Is that true or false? If a figure is not regular, then it's not equilateral or equiangular. Well, that again is true because that's the definition. Okay? If it's not regular, then it cannot be both equilateral and equiangular. And finally, we want to take the contrapositive. And so this is where we take the converse, and we take the converse and we put nots in. So if a figure is not equilateral, and equiangular, then it is not regular. And we want to know, is that true or false? So if a figure is not equilateral and equiangular, then it is not regular. Again, that is also true because that's just the definition. Right, to the back, we're going to keep doing this. The original statement. If two angles are vertical, then they are congruent to each other. Well, that's true, right? We know that vertical angles are congruent. So now we want the converse of that. The converse, I trade places with the hypothesis and the conclusion. So it would say if two angles are congruent, then they are vertical. Is that true or false? Well, are the only congruent angles out there vertical? No. So this would be false. If it's false, we have to give a counterexample. So we could have a linear pair where both our angles are 90 degrees. So we could have a linear pair where both angles are 90 degrees. The two angles would be congruent, but they're not vertical, they're a linear pair. So now we want to take the inverse of this. The inverse is going to say if two angles are not vertical, then they are not congruent. Remember? So the inverse, we take the original statement and we put nots in them. So is that true or false? Okay. Well, if two angles are not vertical, then they are not congruent. Again, I can have congruent angles that are not vertical, so this is also false. So we want to give a counterexample. Okay. I could use the exact same counterexample, couldn't I? A linear pair where both angles are 90 degrees. So now we want the contrapositive. The contrapositive, okay, would state if two angles are not congruent, then they are not vertical. So we want to classify that as true or false. If two angles are not congruent, they're not vertical. Well, that's going to be true because if they're not congruent, they can't be vertical because we know vertical have to be congruent. All right, so now we're going to talk about rewriting general statements as conditionals and then classify as either true or false. So now they just give me a statement. Two angles which are right angles are congruent to each other. So the original statement would say if two angles are right, then they are congruent. Is that true or false? If two angles are right, then they are congruent. They're both right angles, so they're the same. That's true. So now let's look at the converse. So the converse, I trade places with the hypothesis and the conclusion. So if two angles are congruent, then they are right angles. Well, this is saying that the only angles that are congruent are right angles. We know that's false because we know that vertical angles are congruent. So this is a false. So now we want to take the inverse. So the inverse, we take the original statement and we just put nots in. So the original statement, if two angles are right, so it's going to say if two angles are not right, then they are not congruent. And we want to know, is this true or false? Okay, so this is saying that only right angles are congruent. Well, I know that that's not true. I could have two angles that are 45 degrees be vertical and congruent, so this is false. And so then we want to write the contrapositive. Okay. So the contrapositive would say if two angles are not congruent, so we take our converse and put the knots in. So the converse said if two angles are congruent, so this is now going to say if two angles are not congruent, are not congruent. Two angles are not congruent. Okay, so the converse said if two angles are congruent, so I made it say if two angles were not congruent, then they are right angles. So then it's going to say then they are not right angles. True or false? If two angles are not congruent, then they are not right angles. Well, that's true, because if they were going to be right angles, they would have to be congruent to each other. So now let's try it with something that's not math related. Okay. So all whales are mammals. I want to change that to an if then. So I could put if it's a whale, then it's a mammal. So if it's a whale, then it's a mammal. True or false? Okay, if it's a whale, then it's a mammal. Okay, well, that's true. So true. So now we're going to do the converse. So now we're going to trade places with the hypothesis and the conclusion. So if it's a mammal, then it's a whale. True or false? Right? Are whales the only mammals? Absolutely not. So I know that's false. Take the inverse. So this is where we take the original and we put nots. So the original said if it's a whale, so this is going to say if it's not a whale, then it's not a mammal. True or false? Again, just because it's not a whale doesn't mean it can't be a mammal, because there are other mammals besides whales. So again, this is false. And finally, the contrapositive. The contrapositive is going to say if it's not a mammal, right, if it's not a mammal, then it's not a whale. Well, that would have to be true, because if it's not a mammal, there's no way it can be a whale, because we know that whales are mammals. Okay? So true. All right. All right, let's keep going. So next it tells me two statements are considered equivalent statements if they are both true or both false. So we would have equivalent statements if they're both true or they're both false. Original conditional is logically equivalent to the contrapositive. Original and contrapositive are either both true or both false. So let's go back and look at this, all of our examples. Here our original was true, the contrapositive was true. Example 5, the original statement was true, the contrapositive was true. 6, the original statement was true, the contrapositive was true. So that's what we're saying there, that if we know that the original statement is true, then we automatically know that the contrapositive is also true. If the original statement is false, we automatically know that the contrapositive is false. So then the converse is logically conditional to the inverse. So the converse are both either true or both false. So again, let's go back and look at those examples. So example number 4, the converse was false, the inverse was false. Example number 5, the converse was false, the inverse was false. Example 6, the converse was false, the inverse was false. Right? So once I know that my converse is false, I automatically know my inverse will be false as well. If I know that my converse is true, then I automatically know my inverse is true. All right, then we have a special note. So it's called hitting the jackpot for a conditional statement. If all 4 versions are logically equivalent to each other, okay, then that's what we would say we have hit the jackpot. Everything was true. Okay. This usually happens in geometry when the original statement is a well-written definition. Going back to which of our examples was true for all four versions. Okay. So example number 1, nope. Example number 2, example number 3, look, true, 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 true. If a figure is regular, then it is equilateral and equiangular. So example number 3, we said, was true for all four versions because it defined the term, okay? It defined the term regular figures, right? When a conditional and converse are both true, we can write it as a biconditional, which contains an if and only if. Okay? The notation for that, okay, you can, instead of writing out if and only if, you could also write this. It's going to work just for a few minutes for me, as IFF, or you might sometimes see these arrows. So an equal sign with an arrow on both ends. That means if and only if. So what can be written as biconditionals? Valid definitions can be written as biconditionals. Right? So like, let's look at one. The definition of perpendicular lines. If two lines intersect to form a right angle, then they are perpendicular. The converse, if two lines are perpendicular, then they intersect to form a right angle. Both of those are true, right? So the biconditional would say two lines are perpendicular if and only if, and so I am going to abbreviate that with IFF, they intersect to form a right angle. Okay? And this is the definition of perpendicular. Right? All right, so that is 2.2, day 1. Let me know if you have questions.